Swayam Prabha. Digital India. Educated India.
Okay, so we'll talk about digital signature scheme. So this is used for authentication purpose. So this is under public key setup. So we have two party, Alice and Bob, and they are communicating over a public channel. Now Alice wants to send a message to Bob, and Bob wants to ensure that the message is really coming from Alice. So this authentication has to be preserved. So now the digital signature is the public key setup. Now Alice is sending a message to Bob. So Alice has to sign on the message. So this setup phase has to done by Alice. So in the setup phase, Alice has to generate this EA DA. So Alice public key and Alice private key. Okay, and then Alice can encrypt this message using the Alice public key. Alice public key private key. So this is the signature. So this is Alice signature on this message, and Alice is sending to this message to Bob. And Bob has this Alice public key, and Bob can decrypt it and verify this message is coming from Alice. This is the authentication. Okay, now let us talk about RSA signature scheme. Okay, so in RSA, we have to do the RSA setup. So that setup who will do now, because Alice wants to send a message to Bob. So Alice has to get her own public key private key pair. So this setup has to be done by Alice. Then only Alice can sign. After generating the public key private key pair, then only Alice can sign on the message using Alice private key. Okay, so this is the setup phase or key generation phase done by the Alice. So first of all, Alice will choose 2 prime PQ and compute. This is the RSA crypto system. So compute this product n equal to PQ, and then compute the phi n, Euler phi function, p minus 1 q minus 1, and then Alice choose a E such that GCD of E comma phi n is 1. So this is required to ensure that this E has an inverse under mod phi n, and that inverse we denote by D. So we find the inverse of E, and that will exist because this GCD is 1. So Alice has to find this D, and this D can be get by using the extended Euclidean algorithm such that ED is congruent to 1 mod phi n. Okay. So this is the setup phase. So once the setup phase is done, once Alice run this setup phase, so Alice is having this key set. So this key set is basically consist of this N, P, Q, ED, this ED, such that ED is congruent to 1 mod phi n, 1 mod phi n. Okay. So a key is basically this tuple. So key is PQ. So N PQ, then ED. So among this which are the public, only N and E are public key of Alice. So, this is E of A, public key of Alice, this is N and E, and remaining this P, Q, D all are secret key of Alice. So, that is basically D of A, secret key of Alice, this is P, Q, D. Okay. So, but here we can change the role, because we need this ED is congruent to 1 mod phi n. So, this is the beauty of RSA crypto system, this is very symmetric, we can keep one as a public key, other as a private key. Anyway, so we are using E as a public key and D as a secret key. Okay. So, now this is the key setup is done. Now, the plain text space, plain text is coming from Zn. So, Alice choose this plain text M, this message. Now, Alice wants to encrypt this message, Alice wants to sign on this message. So, how Alice will sign? Alice will do the RSA encryption using the Alice secret key, that is the secret to the Alice. So, that Alice only can do digital signature. So, the signature can be done only that person. So, that means we have to do something with the secret, which is typically secret to that person. So, that is typically the signature, and that is the secret key. So, Alice will do the RSA encryption on this message using Alice secret key. So, this is basically M to the power D mod n. So, this is the RSA encryption, but using the secret key of Alice. So, this is the signature part. So, Alice is signing on the message. So, this is Alice signature. Okay. So, then Alice is sending this signature, this is now Y to Bob. So, Bob is having Alice public parameter. So, this is N E, because this is public, anybody can verify this, anybody can do this verification. So, Oscar also having this E of A. So, Oscar also can verify this message is coming from Alice. So, authentication can be done by Oscar also. Okay. So, Bob is receiving this. Now, upon receiving this, so Bob is getting Y, this signature or the ciphertext we can say. So, now what Bob will do? Bob will decrypt it using the public key of Alice. This is the RSA decryption. So, Bob will decrypt this Y using the public key of Alice. So, this is the RSA decryption, this is basically Y to the power E mod n. So, now how it will give us M, because this is Y is basically what? Y is M to the power D, now to the power E mod n. So, this is basically M to the power E D mod n. Now, this is the RSA decryption. So, we have already seen this is just we know that E D is congruent to 1 mod phi n. So, that means E D can be written as k phi n plus 1. So, if we write this, then this is basically M to the power k phi n plus 1 mod n. So, this can be written as M to the power phi n mod n to the power k into M. This is mod n. Now, if we choose n such that n and m are relatively prime, they are co-prime, then by this is the Euler's theorem, this is 1. So, this is basically m. So, now Alice got the message, Bob got the message, and if Alice is sending message also along with this, Bob can compare this and Bob can ensure that the message is coming from Alice. So, this is a typical RSA signature scheme. Okay. So, now we will formally define what do you mean by a signature scheme. So, let us just formally define what is a signature scheme. So, it is basically a 5 tuple like encryption scheme, it was a 5 tuple. In encryption scheme we have P, C, ciphertext space, key space, this is the encryption scheme. So, in encryption scheme we have a plain text space, ciphertext space, key space, and we have set of encryption function and we have set of decryption function, this 5 tuple. So, such that for every key from the key space there must exist an encryption algorithm from this set of all encryption algorithms such that, and a decryption corresponding decryption algorithm dk, dk. So, better we use capital K, capital E, ek and dk from this decryption set of all decryption algorithm such that dk of ek of m should give us m, and this should be true for all m belongs to the plain text. So, this is the encryption scheme. So, if and provided this ek dk should be easy function. Easy function means it should be polynomically, it should not be hard. This ek dk should be feasible function. I mean, it should not be a hard problem like one way function like that. Okay. So, it should be a this ek dk, calculating ek dk. So, if you have a message you should able to encrypt it. So, it could be DES, AES, or it could be any public key. So, encryption algorithm should be should give us the ciphertext, and on this decryption algorithm should give us the plain text back. So, this is the encryption scheme. On the other hand, so signature scheme is also a 5 tuple. So, the signature scheme signature scheme is also 5 tuple. So, we have plain text space, and instead of ciphertext space we have a signature space, as I mean the signature, all possible signature. So, this is basically set of all possible signature, set of all possible signatures. Okay. And we have key space, and we have the signature algorithm or signing algorithm, and we have verification algorithm V. So, this is key space, set of all possible key, and this is the all possible signature algorithm, set of all possible signature algorithm, and this is similarly set of all possible verification algorithm. Verification algorithms. Okay. So, this 5 tuple such that for a given k key, so for each k coming from this key space, there must exist a signature algorithm from this S, and a corresponding verification algorithm from this V such that now signature, this is a mapping from where to where. So, signature of K, it is basically a function from plain text space to this set of all signatures, and the verification is basically it is taking the plain text space and the signature, and it is giving us basically either true or false, authenticated or not authenticated. Okay. So, now okay, so now this verification should be done like this. So, following so for every x, plain text, and for every signature is coming from A y. So, this must be true. Verification of x comma y is true if this y is the signature of x. So, if y was signed, x was signed and this is the signature, and false if this is not y. Okay. So, this is the formal definition of a signature scheme. So, it is basically a 5 tuple, and for each, so it is, this is the plain text space. Okay. So, this is the set of all possible signature, and this is the key space, this is the set of all possible signature algorithm, and this is the set of all verification algorithm. So, if a message was signed by a key, using a key, and it give a signature y, then we should able to verify it. So, it should give us a true if it is a signature basically, otherwise it should give us a false. Okay. So, now let us talk about this what we had discussed, RSA signature based on this 5 tuples. So, what are they for RSA signature scheme? So, okay. So, for RSA signature, so this is the formal way we are defining the RSA signature scheme. So, in RSA signature, P is equal to A is equal to, so this is A is equal to ZP, sorry Zn. So, and N is equal to that 2 P into Q, 2 prime, and the key space is basically this set N comma P comma Q comma ED such that ED is congruent to 1 mod phi n. Okay, and we know these and these are public parameter, and this is the private parameter. So, now if we choose a key N P Q E D, so how we define the signature? So, signature using this key on the message X, where X is coming from ZP. So, this is basically x to the power A, sorry, x to the power D. So, D is the public key, D is the secret key of of the sender, that is Alice mod n. Okay, so this is the signature. Now, how one can do the verification? So, verification algorithm is, so if we have given xy, so it is true if and only if x is congruent to y to the power, so d e y to the power e mod n, and y is basically x y both are coming from z n. Okay. So, this is the RSA signature scheme in the formal way. Now, we will talk about Elgamal signature scheme. Okay, so just to quickly talk about Elgamal signature scheme. Elgamal okay, so let us just quickly recap what is the Elgamal crypto system. So, for Elgamal crypto system, so we have two party Alice and Bob. So, they are communicating over this public channel. Now, Alice wants to send a message to Bob. So, in Elgamal it is based on the discrete lock problem is hard. So, yeah, so for Elgamal we need to show Elgamal signature scheme over ZP. So, this is the signature. So, this Alice has to do this setup phase. So, Alice and Bob, so Alice has to run this setup phase in order to generate Alice EA DA, Alice public key and private key paired. Okay. So, Alice will choose a prime, let P be a large prime, so that the discrete lock problem is hard, and so Alice will, so then ZP star is a cyclic group. So, this is basically ZP minus 0. So, Alice choose a generator, alpha is a primitive element or generator of this group. Now, Alice chooses secret. This is the key generation of the key generation phase of the Elgamal crypto system, and this has to be done by the this setup phase has to be run by the Alice, because Alice wants to sign on the message. Okay. So, Alice will choose a which is basically 0 less than a less than equal to p minus 2, and then Alice will compute this beta. So, beta is equal to alpha to the power a mod p. So, this is the key generation step. Once it is done, then the setup phase is ready. So, key generation is done. So, E of A is basically, so a key sets. So, this is the key space. Key space is basically P alpha A beta, where beta is basically congruent to alpha to the power a mod p. So, now this is the, so a typical key is basically p alpha a beta. So, among this, so this is the secret key. So, this is d of a. So, d of a is basically a, and remaining are all public key of Alice. So, p alpha beta. So, these are all public key of Alice, and only A is the secret key of Alice, and this is the this will be used by the signature purpose, because this is the secret to the Alice. Okay. So, now what is the signature? So, now plain text space is what? So, let us remove this. Okay. So, plain text space is basically Zn star, sorry, Zp star. Did I use n in here? No, Zp star, and the set of all signatures is basically Zp star cross Zp minus 1. This is the set of all signatures. Okay. So, now Alice is choosing a k, and Alice has to sign on the message using this k. So, suppose Alice is choosing a plain text from this Zp star. This is the message of the plain text, and this Alice wants to sign on this plain text. Now, for this is capital K. Now, for L-Gamal crypto system, so there is another secret, another randomness is there, which Alice can choose, which the encryptor can choose. So, here encryptor is Alice or signer. So, Alice can choose a k. So, Alice choose a random number, choose a random k from Zp minus 1 star. So, this is a random number Alice is choosing, and then Alice is signing on the message. So, here is Bob. Now, Alice is signing on the message using this capital K. So, using this B of A and x comma k. So, this is basically gamma delta. So, this has two part, like L-Gamal crypto system has two part y1 y2 for the ciphertext. So, here also in the signature we have two part. This is the Zp star cross Zp minus 1. So, this is gamma, this is delta. Now, what is gamma? Gamma is basically, so the gamma is basically alpha to the power k mod p, and delta is basically x minus a gamma k inverse mod p minus 1. Okay. So, alpha is with Alice, so alpha is the public parameter. So, this is the secret thing Alice is using for this signature. So, this two is sending to Bob. So, now how Bob will verify? So, the verification is basically so Bob is receiving this delta and gamma. So, how Bob will verify? So, Bob will just use this key, the secret key, the public key of Alice, E of Alice, and then this x and delta this, and Bob will compute this basically beta to the power gamma and gamma to the power delta, and if this is congruent to alpha to the power x mod p, then the verification is done. So, Bob will compute beta, beta is public parameter, beta to the power gamma, gamma it is the signature part, and gamma to the power delta, it should be congruent to this. So, why it is true? So, basically we can just simplify this. So, beta is basically alpha to the power a. So, it is basically, if we just calculate this, alpha to the power a gamma into, so this gamma is basically alpha to the power k. So, it is basically alpha to the power k delta, and this is basically alpha to the power a gamma plus k delta. Now, if you come here in this equation, if you multiply both sides by k, so k delta is equal to x minus a gamma under mod p minus 1. So, k delta plus a gamma is basically x. So, this should be equal to congruent to alpha to the power x, which is basically alpha to the power x mod p. So, the verification is done by this. So, let us take a quick example. For this Elgamal signature scheme. Okay, suppose suppose Alice choose this P 467 and Alice choose a generator for this ZP star, and Alice choose a secret key 127, and Alice compute beta is equal to alpha to the power a mod p. So, this is basically 2 to the power 127 mod 467. So, this is basically 132, and suppose Alice wants to sign a message which is basically 100. So, now Alice has to choose a k which is a random number. So, Alice is choosing say this k. Now, so this k has to be chosen such that it has inverse. So, that also you have to take care. So, now Alice is computing gamma. So, gamma is basically 2 to the power alpha to the power k mod p. So, mod 467 which is basically 29, and also delta is basically x minus 127 into 29 to 431 mod 466 which is 51. So, this Alice is sending to Bob 29 and 51. This is gamma and delta. So, after receiving this, what Bob will do? Bob will compute this 132 to the power 29 and 29 to the power 51 and check whether this is equal to, this is basically 189 mod 467, and also compute alpha to the power x. So, this is basically also 17 mod 467. So, these two are same. So, the authentication is done. So, this signature is valid. So, the signature is valid. So, this is the Elgamal signature scheme over ZP. Thank you.